Welcome to the 13th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. This is a summary of Chapter 8. Chapter 8 is a rather small and short chapter. It summarizes our four operator identities, which are the Leibniz rule, the Hadamard lemma, the Baker-Campbell-Hausdorff formula, and the exponential disentangling identity. So Chapter 8 is summary of fundamental operator identities. As I mentioned, we have the four of them: Leibniz product rule, Hadamard lemma, Baker-Campbell-Hausdorff formula, and exponential disentangling identity. Let's go browse through the chapter. This chapter starts off with the quote from Georgia O'Keeffe: the abstraction is often the most definite form for the intangible thing in myself. So in this chapter, we really just summarize the four different fundamental identities. We have the Leibniz product rule. And for those of you that are interested in calculus or no calculus, it turns out this Leibniz product rule is sufficient to work through and define an abstractly defined derivative. And that is why, if you know about calculus, you find commutators of p with a function of x will act like a derivative of that function. You can see an example of that in equation 8.2, which shows when you evaluate a commutator of a to the n with b, you get n times the commutator of a with b times a to the n minus 1. So if the commutator of a with b is a number, like it is with position and momentum, then you end up getting something that acts like a derivative. Okay. In addition, there's another identity that is an important one, but one that we don't use very much, called the Jacobi identity, and we show that one here as well. The second fundamental identity is the Hadamard lemma. This is probably the most important identity that we have in the class. We do most of our calculations using the Hadamard identity. In the Weil form, where the commutator of a with b commutes with everything else, it takes a much simpler form. We can rearrange it into something called an exponential reordering identity, and we also recognize that it has this braiding identity. So when you do a Hadamard lemma, you can actually put it inside the argument of functions, and that's where it becomes a very, very powerful identity. The next identity that we have is the Baker-Campbell-Hausdorff formula. This is one where it's really only useful if the nested commutators eventually truncate and are equal to 0. And the most famous form of that is in the Weil form, where the commutator of a with b commutes with everything. But there are situations where you might get that truncation at the second or third order as well. And it has a couple of different forms. There's the traditional Baker-Campbell-Hausdorff formula, where you write it as an exponential of a sum of all of the different terms. And then there's a Zassenhaus form, where you write it as an exponential of a product of different terms. And we talk about both of those forms in this chapter. And then the final one are the exponential disentangling identities. We work them out for the special unitary group and for the symplectic group, both in 2 dimensions. Those are the only cases that we really need. SU2 is important for anything involving angular momentum, and we use that to calculate the spherical harmonics in Chapter 9. And the symplectic group is useful for things involving the harmonic oscillator, and we use that identity a lot when we were talking about squeeze states. So this is a nice place to go to if you want to immediately grab one of those identities. You have a place here where they're all available and you can grab them. Hey guys, let's do quantum right.